I'm going to speak to you today about the compact processor and the production of carbon black master batch on the compact processor. Some of this is repeated information, but it'd be useful for those of you who haven't been introduced to the compact processor technology. The agenda today will be a quick company overview, some key applications of the compact processor. I'm going to explain what the compact processor is. I'm going to explain how it mixes. And then finally, I'm going to show you some slides where we've worked with carbon black on the compact processor. And finally, some of the advantages of that compact processor for products like carbon black. Farrel Permini belongs to a larger group, HF Mixing Group. I won't go into all the detail, but HF Mixing Group is effectively Farrel Permini and what was the Werner Fleider arm of, or Werner Fleider's rubber mixing arm. In 2010, HF Mixing Group was formed out of all these companies to take the best of the best in both rubber and plastics mixing to create specific machines to satisfy customers' requirements. 2016, last year, HF Mixing Group built a bespoke factory in the US to house Farrel Permini, which is where we're now working from. So most of the machinery we make and manufacture comes from the US. That said, HF Mixing Group is worldwide. We have over 1,000 employees. We have production facilities in Germany, in the United Kingdom, the US, Italy, Slovakia, China, and India. We have sales offices in US, France, Spain, Czech Republic, and Singapore. And our turnover last year was well over $430 million US. As I described in the slide previous, Farrel Permini belongs to HF Mixing Group, and HF Mixing Group is 3 companies brought together to form one big group. In 2011, we decided to focus our business interests in 2 areas. One was discontinuous mixing, which will be to you guys the Banbury mixer and the Intermix, and the continuous mixing business group, which is the compact processor and the continuous mixer. And that's what I represent here today is Farrel Permini. Ourselves, the continuous mixer business unit, as I said, is in the US. We have over 100 employees there. As I said, we've just moved into a new $10 million facility in 2016. And we produce compact processors, continuous mixers, extruders, large melt pumps, and very large pelletizers. We have representation around the world, as I said, in the US, the UK, Italy, and in Asia. And some of the key applications we're involved with, we'll come to on the next slide. Calcium carbonate master batches and compounds, white master batches, TiO2 and calcium carbonate blends, carbon black master batches, HFFR compounds, flexible PVCs, both filled, cable and medical grades, and then finally sound deadening materials. You can see the emphasis here is on 2 things. 1 is heavily filled materials, and 2 is temperature sensitive products. That's where we sell our most machines to. Developing markets for us, though, wood flour composites, biopolymers, rigid PVCs, thermoplastic elastomers, and rubber compounds. Some of these are reintroductions for us. Some of these are markets that we left and we're now being reintroduced to. Excuse me. So, what is a compact processor? It's effectively 2 machines together. On the top, we have a mixer, and below, we have a standard single-screw extruder. And basically, what we're doing here is we're separating 2 processes. One is the top part, which is the mixing process. The bottom part is the pressurization, the pelletization process. What this allows us to do is widen the operating window of the single machine to do many materials and many products without changing the mechanical configuration. Compact processors are usually installed with feeder systems, screen changers, and pelletizers, and we incorporate all this into one control system. And I notice some of our partners here, Marg and Nordson and Econ, we incorporate their products into our line to create a full compounding or masterbatch system. We can go even further than that as well. We can incorporate materials handling, bagging stations, and weighing and feeding. Principles of operation. We usually do this slide comparing with twin screws. We all know what a twin screw extruder is. It's two screws in a barrel, co-rotating. The Farrel system has two rotors rather than screws, and those screws are non-intermeshing. They're counter-rotating, and they're supported at each end. And what this allows us to do is to run the machine without any material in. Unlike a single screw or twin screw, you have a cantilever on the screw which potentially can cause pickup of material on the barrel from the screws. With the Farrel system, this doesn't happen because we have both ends of the mixer supported. The machine runs starve fed, and that's to say material is fed in one position only. So we save money on elaborate feed systems and side feeding systems. We only feed material into one feed port. Polymer flows through the machine, or material flows through the machine due to viscosity change. So we're not forcing material through the machine using the screws. We're actually allowing the material to flow through the machine with stiffer material being pushed against the softer material that's molten out of the orifice at the end. As you can see on the two diagrams below, one side you can see is full. The opposite side you can see is less full. You can see underneath the two descriptions where it mentions the orifice. We have a gate on the underside of the mixer which allows us to increase or decrease the fill of the mixer, thus allowing us to do more or less mixing depending on what products we're doing. Mechanical features of the machine. As you can see, it's all on one frame. Everything is installed, both the mixer and the extruder and the control panel. It's electrically heated and water cooled. We have one inlet and outlet for electrical, air, and the water for cooling. And we have a machine-mounted operator's touch view screen, so it's very easy to install, very quick to install. Now we concentrate on just the mixer itself. This is the real important part of the machine. This is the part that does all the work. As you can see from the diagram that's just started there, it has a clamshell opening top, which allows access to the rotors. It has replaceable tool steel liner. We have a single feed port, as we've already mentioned. 3-piece rotors, which can be removed, as you can see in the diagram now. Grease-packed bearings, so we avoid the issues of oil for lubrication. We have a unidrive gearbox. And really, really importantly, we have no expensive thrust bearings. There is very little pressure produced inside the machine, typically less than 1 bar, so we don't need any lateral moving bearings. All we use is radial bearings. We also have the ability to atmospheric vent on this machine as well, because it's a low-pressure system, so we can open a hole in the top of the machine and allow it to breathe. We have multiple zones for heating, but more often than not, the machine is running adiabatically. That's to say that once the machine is heated up at the beginning of the run, it's left to either run at a stable condition or it's put into a cooling mode. The effective length of mixing is 3.5 D. That's very, very short compared to a twin screw extruder. In terms of time-wise, material usually stays inside the mixer for around 15 to 20 seconds. So you can imagine there's a lot of protection for the polymers being processed at a lower heat history, which is also can be a benefit. Machine maintenance. Here we show a picture of our laboratory machine open. You can see the clamshell, and you can have an idea of how easy it is to access, to clean, to take the rotors out, and ultimately reduce downtime for the customers who use this type of technology. The extruder itself is very simple. It's there to convey material only. So you can imagine homogeneous melted material exiting the mixer. It's discharged into the extruder, and then it's fed towards the head, whether that be strand or underwater pelletized or dry face. Ultimately, it's just a conveying system. Very short, 11:1 LD. We have a standard compression ratio, but we can design alternative compression ratios depending on the material to be produced. It's electrically heated and water cooled, although we can do with air cooling as well. We have the option for two-stage extruder, so we can extend the length of the extruder and put a decompression zone on there for additional vacuum venting. And as I said, we can adapt to multiple heads depending on what the pelletizing requirements are for the product. As I mentioned, the machine has a touch view screen, but this is not just ordinary touch view screen. This is a full SCADA package. So it will do historical logging, recipe management. It will collect data with a 1 terabyte drive. The screen itself is Windows-based with Wonderware software that we design in the US, and we can monitor remotely, given permission by the customer, so we can do diagnostic work and checks without sending out engineers on expensive trips. We can also customize that to include things like pelletizers, the control of feed systems, the control of weighing and feeding, and other things as well. So we get to the important part of the mixer itself. I'm going to bring the cursor on here, if I can. No. Okay, you see the feed flights, the mixing section, and then a final pumping section. Basically, the feed flights are there very simply to take the material fed in by a typical loss-in-weight feed system, transfer that to what we call the forward helix, which begins to melt the polymer, starts to disperse the pigments or the powders or the minerals. And then we have a reverse helix, which pushes material back up the machine, creating a kneading action. Ultimately, what we get is a very good mix, a very well dispersed mix, a very well distributed mix in a very, very short space of time. Machine ranges from what we call CP125. The 125 depicts approximately the throughput rate for a nominal product, so that's 125 kilos, right through to 4,000 kilos or 4 tons an hour. This is just on the unitized frame version. We do go higher in throughput rates, all the way up to 15 tons an hour for compounding. I've also highlighted in red here the newest addition to our range, which is the laboratory CP, we call CPX. It's a 35mm mixer and 60mm screw, but I'll go on to describe that in the next slide. We were asked by several larger customers of ours why we didn't have a small laboratory machine. So we answered their prayers and we designed this. It's basically a combined mixer and extruder, close coupled, so there's no discharge distance. Still has the ability to open and close the orifice, so we still have the ability to increase or decrease the working volume inside the machine. And two important factors here. One is that we can change the length of the mixer. We can go from the long version of our mixer to the short version on the same stand. The other important factor is we have the same SCADA system, which can be remotely accessed by the customer. So you can remotely access this system by a tablet, a laptop, wherever you are in the world, to check or to demonstrate what you have in your laboratory. The machine does approximately 10 to 30 kilos an hour, so can, as a push, be used for production on small master batch, small batch materials and things like that. So, how does it mix? The typical diagram is showing both dispersive and distributive mixing. It's the same for every system, same for all technologies. Ideally, we want to be in the bottom right-hand corner with good distributive mixing and good dispersive mixing. And we feel that with the Farrel mixer, this is what we achieve, certainly for the high-filled products. How we achieve this on the mixer, you can see from the diagram here, the dispersive component takes place on the forward helix. You can see the laser. I'm just going to try and find the laser so I can point. Maybe not. Sorry, you can see on the forward helix, the section through. Above, you can see that the rotors are in phase. They're actually tip to tip. This is a part of the design of the actual rotor itself. But what's important is you can see the rolling pools of material are closed inside each chamber. There's not much chance for interaction between one chamber to the other side. So the window of interaction is very minimal. This is where all the dispersive action takes place, where the wiping of material against the wall of the chamber and material against itself takes place. For the distributive component of the mixing, we can see that takes place on the reverse helix. So you can see the section through is on the second part of the mixing rotor, where the design of the rotor is out of phase or not tip to tip. And here you can see instantly what happens. Material is able to transfer from one side of the mixer to the other. So combine that with the reverse motion of the reverse helix, you can imagine a kneading action taking place inside the mixer. So we're not just using the mixer to push material through, we're actually moving material inside. There's a very, very high free volume inside the mixer which allows this action to take place. Just to give you an idea of what happens in the mixer, we took a sample of material after the machine was stopped to show you how the formation of a homogeneous mix is made. You can see pellets coming into the machine from the right-hand side with powder undispersed. As you can see the shape of the forward helix taking place, you can see material being melted out and mixed. You can almost see the transition section where the gap is on the top part of the section. And then finally the reverse helix where the material is completely homogeneously mixed. And then finally the discharge section where you see a very little amount of material. Material has been taken out of the mixer through gravity to the extruder. We also took an opportunity to cut these sections through to see how the material is densified as it goes down the mixer. From where it feeds in on the right to where it discharges on the left. And on the left you can clearly see the rolling pools of material. And finally we have the discharge orifice. The thing that makes the mixer unique is the ability to close and open this orifice to allow the material to be, or the amount of material to increase and decrease inside the mixer, and therefore affecting how much mixing takes place or how much shear is input into the material. Now you can see on the bottom video here, there, a typical discharge of black masterbatch into the extruder. As far as rotors are concerned, we generally supply the machine with only one set of rotors, and that's dedicated to the products the customer wants to run. Although we have two different designs, the Style 15 and the Style 7. The 15 is typically what we call general purpose. It's there for all polyolefin applications. It will go through the complete range, right from EVAs right through to some engineering resins. And then below we have what we call shear-sensitive rotors. These were the first generation of rotors, and we use these for temperature-sensitive applications such as rigid PVCs. On occasions, some flame retardants, but more often than not, we will make a combination of the two. So you see the two different styles of rotor. Where they differ is on the angle of the forward and reverse helix. On the less intensive rotor, the Style 7, you see the helix is very gradual and very long. And on the more intensive rotor, the Style 15, you can see the angle of the helix is very short, thus giving an additional input of shear very quickly as the material gets into the mixing section. On this particular slide, we show a combination of the two rotors. For things like carbon blacks, where we have to control the temperature but provide a very good dispersion, we combine the two rotors to give us the optimum results. And I will describe some of the findings we made in a later slide, which is part of the carbon black type presentation. Someone asked me yesterday about wear protection for products and asked me how sensitive the mixer was to abrasive materials. As one of Farrel's key factors is material selection. Ultimately, we're mechanical engineers. We build machines. And one of the key areas of our research and development is finding new materials to put on the rotors to make the rotors last as long as possible. And here in the slide, you can see the three options that we offer at the moment. The top one is our standard chrome plate, and this would be for general purpose applications for most colour masterbatches, for most white masterbatches depending on the amount of fill. And then we go to the HUF thermal spray coating, which is a level up of wear protection, which we use for highly filled materials, calcium carbonate, high fills of white masterbatch TiO2s. And then finally, we have our cladded rotor, which has an undercut, which allows a welded hard surface to be placed underneath the chrome. And this we offer to our highest abrasion applications, such as iron oxides and barium sulfates. And in some cases, we offer this also to the highly filled calcium carbonate market and the TiO2 market. But ultimately, we have a full range of wear protection, and we also have next generations of wear protection on the way, which will probably be presented in the next ICMBA seminar. So, processing flexibility. Most systems have the same independent variables that can be changed, such as production rate, rotor speed, and machine temperatures. Ultimately, two things we have. One is the fact that we separate the system of pressurization and mixing, which allows us a greater operating window. And secondly, the orifice, which allows us to control the amount of material that's inside the mixer at any one time. With these two possibilities, the separation and the orifice, it gives us a very, very wide range of operation for a very wide range of products without changing the machine mechanically. So that's to say we can go from a PVC to a polyolefin, to a polypropylene, to an engineering resin, without actually physically changing too much with the machine. It gives you a very, very versatile piece of equipment. Other processing points to raise, as I said in the previous slide, we have atmospheric venting. So because the mixer has been separated from the pelletization process, it's very low pressure inside the mixer. It allows us to open up the end of the mixer to atmospheric, either a degassing system or a defuming system, but we don't require any expensive vacuum systems. Typically, we can take a calcium carbonate 80%. Depending on the type of calcium carbonate, we can take it below 200 ppm in terms of the moisture content. So that's the level of venting we can achieve with the mixer with the atmospheric vent. We also have the ability to put mixing dams inside the machine as well. I'm going to show you that on the next slide. I stopped it there just to show what I mean. The top of the mixer itself is segmented, and there are plates that we can take out and move. And you can see at the far right here, the hole which houses the vent. On the next plate, you can see a dam. And at the bottom of the dam, you can see what's like a pin. And the pin basically inserts into the machine, and it encloses the barrel, increasing the surface area and increasing the amount of time the material is being passed between the rotor blade or the rotor tip and the wall of the chamber. So we can position this dam up and down the segmented section of the chamber, therefore increasing or decreasing the amount of additional dispersion that might be required. Finally, as an addition to what I said earlier, we provide process solutions. So we don't just provide equipment, we provide designs for buildings, designs for mixing towers. Ultimately, we can supply locally the services to build those mixing towers and design those mixing systems. Not quite turnkey, but to provide a complete system from refill of the silos right through to bagging off of the pellets. We have laboratory facilities both in the US and in the UK. I put the slide up for the UK, as most of the Indian customers tend to come to the UK for their trials. We don't have a benchtop mixer or a small CP in our laboratory. Basically, we've got in there a production-sized machine. And the reason we do this is to give our customers the ability to see not just the capabilities of the mixer, but to also see the full line in action. They're effectively seeing what they would see on their plant if they purchase this type of technology. And being able to demonstrate that fully gives the customer a little bit more satisfaction that not only they're buying the right equipment, but they're dealing with the right people as well. As you can see, we have the full range of rotors. We have both the standard extruder and the longer two-stage extruder. We also have strand and underwater pelletizing and a fully functioning loss-in-weight feed system with 6 feeders. We've actually got 7 feeders. We've got a weigh belt feeder as well, but it gives the maximum in terms of flexibility for our customers to try their materials and do testing in our facility. So that sort of ends the part on the compact processor. I'm just going to do a small presentation on carbon black, really to demonstrate what we can do with the machine and what we have done with the machine in our own laboratory for our own purposes. So briefly, what is carbon black masterbatch? I think most of us already know that. It's ultimately a concentration of carbon black in a carrier, between 20 and 50% depending on the application and the particle size. We use carbon black typically as a modifier or UV stabilizer or to provide conductivity. Applications, again, where we've had presentations on pigments and carbon blacks, so you know all the applications. Typically film, automotive, pipe and cable, depending again on the type of carbon black and the type of carrier. Just to give you an idea of the structure of carbon black, it has a primary particle, an aggregate and a agglomerate. When any system is mixing carbon black, the objective is to get good dispersion. Good dispersion is breaking up those agglomerates into the aggregates and distributing those aggregates evenly in the matrix of polymer to get a good dispersion. Ultimately, we can't go any smaller than that aggregate. That's as small as we can go. In terms of the types of carbon black, they range from large particle size down to small particle size. The smaller the particle size, the better the coloration, the better the mechanical properties, and the better the ability to resist UV. Criteria for producing carbon black masterbatch. This is our feeling from Farrel Pamini. Gradual shear input, excellent temperature control, good distribution, good incorporation, wetting out of the pigment, and finally, very good dispersion. That's what gets you good carbon black masterbatch. How we achieve this on the CP? Generally, we use style 15-7 rotors, so a combination of the aggressive and the non-aggressive rotor. We put the mixer body temperature very low. We have the ability to get that temperature as low as possible, down to the same temperature your cooling system will provide. We have in the past used chiller systems with a cooling system on the Farrel to get even lower temperatures. We have the ability to cool the inside of the rotors, which means we maximize that ability to cool. So we're cooling the outside of the chamber and the inside of the rotor. We place the orifice at around about 70% or even higher to get the maximum material through the machine. We put the extruder at a very cool temperature to make sure we don't have any hot spots behind the die. We generally process or try to process below 220 degrees C. Obviously, that's dependent again on the particle size of the product and on the carrier of the polymer that we're using as a carrier. Depending on the formulation, we may or may not use a dam. If we need to get additional dispersion, we put a dam in the position, usually as close to the feed section as possible. So here's a summary of some of the tests we've carried out in the laboratory, ranging from a very low quality carbon black master batch with calcium carbonate right through to a reasonable quality P-type black, 40% loading. And you can see the full range of products that we can produce on the CP. Again, I repeat, without changing the machine mechanically. We can do all these products without making any significant mechanical changes. Just to go in a bit more detail, we did a study on polypropylene with 40% P-type black. And we put this slide up just to give you an idea of what we do in the laboratory to tune the product to get the best results. So on the left-hand side, you see the machine parameters that we chose, and on the right-hand side, you see the effects. Ultimately, we're looking at the FPV down the right-hand column, and we're targeting the best possible result there. And in doing so, we went through a process of changing the rotors, changing the rates, the speeds, the metal temperatures. We left the orifice as it was, but we incorporated, in some cases, a dam in several positions. And as you can see, the best option was without the dam in at all. But ultimately, what I'm trying to tell the customers here is we can tune the mixer to produce a product to the best quality without changing things mechanically. And that means you can do a varied range of products, not just P-type blacks, but every black, and tune those products online using the parameters of the machine, again, without changing anything from a mechanical perspective. Finally, in summary, producing a carbon black master batch on a CP gives you versatility, as I said. Lower processing temperatures because the mixer is more free volume. It's producing the mix over a shorter distance so we can discharge at lower temperatures into the extruder. We can reduce material costs. A lot of our customers come with formulations with high amounts of wax in. We can reduce those quantities of wax because ultimately we need the friction inside the machine to produce the homogeneous mix. Again, we can minimize energy usage. Typically, we're only running a machine that is 16 LD long. I would suggest with a carbon black master batch on a single or twin screw, you're almost twice that, if not 3 times that length. And again, as we've described with the machine being easy access, it's cost effective in terms of maintenance. You can see we can take the rotors out. We don't have to replace those rotors. We can repair those. We can bring them back to the factory. It's very easy to run. It's very limited in terms of the amount of downtime you have. I'd just like to say thank you very much for taking the time to listen to me, and if you have any questions about what I've presented, please feel free to ask.
I'm Alok Mathur from Podar Pigments. I just want to ask, what is the life of the rotor?
Depends on the material you're producing. Typically with a carbon black...
40% carbon in polypropylene, if you say.
Sorry, was that carbon black? 40% carbon. Yeah, I would say, typically I would expect 2 years, 18 months to 2 years on the rotor before it requires repair.
2 years.
Generally what we do is we supply the machine with 2 sets of rotors.
Okay.
So ultimately what you have is a quick turnaround when you find you're starting to get wear on the rotor. You can quickly remove one set, replace it with the set you have in stock, and then ship the worn parts back to Farrel, and we would do the repair. But yeah, typically for polypropylene and 40% carbon black, I would expect at least 18 months to 2 years.
2 years. And for TiO2, if we say?
TiO2, yep. Again, we'll probably select a different wear package. We go for something like the HVOF or the undercladded rotor. Again, depending on the product, a quality TiO2, 75%, 80%, I would expect to be getting at least 12 months to 18 months.
Okay.
If it's a lesser TiO2, higher fill levels, then that might be slightly less. But okay. Between probably, certainly 12 months to 18 months, definitely.
Okay, thank you.